Hello, sir. Good morning. Sir, can you hear me? अमित आवाज आ रहा है मेरा? Hello, sir. Good morning.
Hello, good morning. Good morning.
So we are at day 4 of our course.
So, yes, I got your email. So I think because my meeting starts in the afternoon, and if
Yes,
you
sir.
want to after the finishing the first two part, so I think I'm also available. So for personal about action the control.
So in the first half, you will deliver this H infinity, or in the second half?
In the second half. In the second.
Second half. At what time, sir?
It depends on you because my meeting start in the afternoon Italian time, but it depends on we can follow your schedule, and then the first part I can be participating, but the second part I think you arrange it that the topic is related to okay about the time delay. So I think for lecture 11, so it's okay for me. Then, but of course, if the other colleague want also to contribute, it's also fine with me. But yes,
Actually, sir, Dr. Prajapati was asked before for this H infinity control. And as I mentioned you that he has agreed to deliver that talk.
okay.
But
okay, we can if he's available, we can.
sir, what I request you, sir, in the first half, as your session is 10:30 to 12:30, so in the first half, if it is possible, you can deliver something on H infinity control from 12:30 to 1 p.m. Uh, Another 30 minutes you can extend, sir. 30-40 minutes.
Okay. Okay. Up to 1 p.m. It's okay. Okay.
Okay, sir. Okay, sir.
No problem.
So I have requested the participants to join. Sir, it's 10:30 only. If you allow, we can wait for another minute, 1 or 2 minutes, and let
Sure.
let them
Okay.
join. Yeah.
Okay. Thank you.
Okay, sir. We can start the sessions, and good morning to one and all again. And I again welcome our foreign experts, Professor Hamid Raza Karimi, sir. Uh, on day 4 of 1 week GiAN course on resilient control of cyber physical systems. In this today's first hub sessions, Sir is going to deliver his talk on cyber attacks, event-based fault-tolerant control, and brief introductions followed by the applications of H-infinity control. So with this, I request respected Sir to please continue the sessions.
Okay, thank you very much. Good morning, everyone. So let's continue our lecture on the topic of the cybersecurity. So basically for today, I want to talk about two particular issues. So one issue is about the effect of the cyber attack. Basically, we call it as a measurement outliers. So in some applications to the CPS and also the mobile, such as mobile robot. And then I will talk about some new technology we have for the fusion estimation for enhancing this mobile robot localization under all of these features. But this presentation today, so that first I'm going to give the introduction to the topic. So because this is a very interesting topic for research and industry. Another side, if we look at some application to the autonomous cars or autonomous vehicles, and we can see that there is some standards basically for the enhancing the safety and security as we discussed yesterday. So yesterday we discussed some standards that we have basically for the autonomous driving. And for this particular case, so SAE J3016 is about the level of automated driving. So if we look at the level of the driving from the no automation, level zeros, to level 1 is a driver assistant, level 2 is a partial automation. So now you can see that the system support you during the driving. But nowadays the technology moves on to the full automation. It means the conditional automation, high automation, and also the full automation to level 5. So if you want to enhance this kind of the autonomy in the automated driving, so one challenge is about the safety and also some issues we have about the measurement. Because important issues in the cyber attacks and cyber security is the malfunction of your sensor data. And if the sensor data is under cyber attack, so how we can guarantee the safety of the autonomous automated driving? And the challenging part is focusing on some outliers. Outliers on the sensor data include the fault, includes the attacks, and not the sensor should be able, basically the system should be able to handle this kind of the misinformation we have from the sensor data. So now we can see that the topic is very challenging. Another topic, if we look at the sensor data, because in this particular application, so you need to look at the in order to precise a vehicle direct environment object detection sensor can be used. So in this particular case, so if we look at basically some distinction between the two sets of a sensor. So we have a passive sensors. It means that you can detect existing energy like light or radiation. So these passive sensors are reflecting from the object in the environment. So the passive sensor could be like a CCD camera or CMOS camera. So that's it. These are the passive sensors. We have another sensor as active sensors. So this kind of the sensors, they send some signal, for example, electromagnetic signal, and then and receive or sense its reflection. So from the sending and also the receiving the signal, so such as the ultrasound sensor or the radar, so we can basically look at the sense of the information. So now you can see that the one CPS system, like a car, is consists of the many sensor technology mounted on the cars, including the passive sensors, active sensors, and now you can see that each sensor has a particular coverage. So in for this case, so we can see that more sensors, more information, but at the same time, there could be more threats, basically to the sensor data. So now today I'm going to tell you that if you have such a, for example, particular sensor, like the active sensor, like the LiDAR, so how you are able to handle the cyber security, so in your sensor data, and then is the car itself can, or the robot itself, it can find a good localization. If the robot or the car can have a good localization in the systems under control, because you can follow the same automated driving. So regarding to the sensor, so basically this could be the one spectrogram of the signal, so based on the wavelength. So now you can see that the different sensor has a different wavelength. So for example, a passive sensor or active sensors, and this kind of basically the spectrum of the signal based on electromagnetic spectrum, it can be used for the perceptional sensors. But this could be the same active sensor. You can see that this here, the sensor can send out, the signal can be sent out, like electromagnetic signal, and then after the hitting on the barrier, the signal can be reflected to the source. So this kind of a transition of the signal, so basically you can calculate one parameter is the time of flight. So the time of flight, you can see the time of flight principle, TOF. So it's one of the key parameter for the sensor, for the active sensor, in order to calculate the distance from the object. Okay, so if the landmark or this point can be detected, the distance can be detected, and then the car can try to consider it to avoid any collision, and therefore this active sensor principle, it works in such a way. So the sensing, the data, it is the main issue we have in this kind of the large scale system. So because in the autonomous cars, so the basically you have maybe partly or even the environment is unknown and environment is dynamic. So now in this unknown or the dynamic environment, so it's very important to simultaneously is to build a map of this environment mapping, and also how the robot or the car can localize itself within the map. So now you can see that the environment mapping and localization is the important aspect. So for the basically the autonomous cars. So the input to perform this simultaneous localization and mapping is the SLAM. So in robotics, so you heard about a SLAM, a keyword. A SLAM is a simultaneous localization and the mapping. So and in this particular case, so you need to look at your sensor data. And then if there is some existing or the pre-existing maps, it may be created by the AI or the human. So you can combine so your sensor data and also pre-existing information. So this could be one unknown environment. You can see, so in this unknown or uncertain environment, there are different cars, the human, And then you can see that if the car want to find the position, the location based on Islam, so this environment is a challenging, and therefore there could be difficulties for to find the precise localization. But anyway, so the sensor on the cars, so they can check it out, basically all basically the safety issues in order to avoid the collision. And then the task is that if your sensors is contain some false information, so how you can still guarantee basically the automated driving for these particular cars. But now you can see that for the high technology, so it's very complex. So it's such a complex environment. So to realize this higher autonomy level, and therefore, how to enhance it? First, we need to come back to the data, to the sensor data, and therefore you need to have a better technology to do the data processing. And therefore, today I'm trying to give a little bit more in the favor of the data in order to do the better estimation of the position of the vehicles. So the position measurement are mainly influenced by the odometry. It means that you can get the position data from the wheel sensors. It's the odometry data information, or you can use the data reckoning. Data reckoning means that you can use some heading sensors. If you are using the heading sensors, so basically, or you can combine the odometry and the reckoning sensors. So the movement of the robot, it means because of this movement, first you can get some data from the wheels. So based on encoded data, and also then you can also use some data from the heading sensors. So the heading sensor, like this information is useful for the rotation. Okay, now you have a position, and also for the other information such as the heading sensors. So then you can also combine or you can integrate it for the position estimation. So this approach, if you want to use it, the data from the wheels, so it's a very straightforward, it's very easy. But the problem is that, so the wheel sensor data for the cars is it could be, there could be the errors in the calculation, and also could become the unbounded if you have some attacks on the sensor data from the wheel. So now you can see that for the vehicle and the robot, if you are using the sensor data from the wheels for the control and the positioning, if there is some cyber security, so the result is not accurate, and even you cannot get any the basic estimation of the position of the car. So this is the reason that the problem of the cybersecurity for the cars is very important. So therefore, we need to find a better technology, better solution for the higher safety. So now you can use another sensor, like a heading sensor. So this heading sensor, like a gyroscope, so this sensor can help to reduce the accumulated errors. But the main problem still remains. But this sentence is very important. Even if you are using the another sensor like a gyroscope in the vehicle or the robot, so the problem cannot be solved because if there is any attacks to the cars, specifically to the sensor, wheel sensors, so all of your information so is not able to give you the precise the localization of the vehicle, and this problem is still remains. So this problem is a big problem. So for the higher automated autonomy in the autonomous driving. So now my presentation today. So I try to tell you the problem and why this kind of issues is important from application, and at least I'll show you some solution how to solve this kind of problem. So let's look at the odometry data. Odometry data, So if you look at this car with the two wheels, so now you can see that the car in the position X, in the direction X, and the direction Y. So there is some position X and Y. At the same time, so this car has a velocity v. You can see it has a velocity v. At the same time, there is some angular velocity, the omega, because of the rotation of the wheels. Okay, so this car, so it has the direct movement, and also there is an orientation, the alpha, because of the rotation of the car. So now based on this information from the wheel information, if you know the speed of the linear speed of the wheel with the VR, and also rotational speed, the omega r, then you need also to look at the alpha. The alpha is the orientation. So if you write down the kinematics, so for this you can I will show you the next. So in this scenario, there are some errors in your calculations. So the error source could be some deterministic errors. So deterministic errors can be eliminated by the calibration. So if you do the sensor calibration, you can remove some determined integration, right? So in this integration, there could be some bias in the calculation of the position. So mechanical problem, misalignment of the wheels. So this misalignment of the wheels for the wheels left and right, they can give you some deterministic errors. So unequal wheel diameter. So if the diameter of the wheel are not equal, they can also give some deterministics. There could be some variation in the convex of the point of the wheel, and so now you can see that there are some major errors. If it goes to some sort of mechanical errors, it can be solved. But if you have some fundamental errors from the computation and also from the sensor data, it's difficult, and therefore you need to pay very carefully. So one of the sensor is useful for the autonomous driving. So it's related to basically to the LiDAR. So basically there could be some advantages. So this kind of the Doppler radar sensors, the advantage is the greater coverage, lower cost, a smaller size, and also lower weight. But there could be some advantage for the Doppler radar sensors. So this radar sensor is widely used in intelligent transportation, space exploration, and also wireless communication. And there is a significant application in mobile robot localization. So we can use a Doppler radar sensor for the estimation, position, and also the heading of the mobile robot. And you can use the information, we call it the Doppler frequency shift measurement information. So the Doppler frequency shift is basically the information you can get from the Doppler radar sensors. And this information, you can combine a feature-based mapping with the landmark, and we can use the Doppler radar. You can do some extended Kalman filtering, and basically, and also there's some other filtering techniques. So now you can see that you can use some advanced estimation. So based on the information you have from the Doppler radar sensors, and even you can combine it with the feature-based mapping you have obtained. So basically, based on some other techniques. Okay, so after this introduction, I want to talk about the localization based on some measurement outlier resistance on the network. So you see, so these outliers, so includes for example, the fault with the data, the measurement. So now you can this robot, you can write the velocity, the y direction, and also the rotational speed based on the omega and also the theta. So now you can see that the kinematics of the robot, it has the two information. One is the x and y, another is the theta. The theta basically shows the orientation, of the basically the robot with respect to X and Y. But at the same time, so the information you have from the mobile robot, so it could be the YR, and also it could be the includes the velocity, the linear velocity v, and also the angular velocity, the omega. So it means that based on these two speed information, so you need to obtain x, y, and the theta. Okay. So now the point is that this linear velocity v and the angular velocity omega, you can get this information, and based on this information, you need to obtain the position x, y, and also the theta is the rotation. So the first assumption is that the displacement and angular velocity of the mobile robot received by the odometric sensors are constant over the sampling time. So we assume that in one sampling time, this information of the displacement and also the two velocities you can obtain. So these are the basic, the constant. So in this case, you can linearize, you can be discretize. You can discretize the kinematics equation in the equation number 2, and the delta t is the sampling time. Okay, so for one sampling time, you can write this to the discrete model for the position and also the angle based on the two velocities, linear velocity and also the angular velocities. But you can see that this model is nonlinear because here you have a sine and a cosine, and therefore this kinematics model is nonlinear. So if you start to represent it in the based on the input and output, you can take the vector x as a position x, y, and the theta, and also you can consider the control input or the input the data is the sampling time multiplied velocity, linear velocity, and sampling time multiplied the angular velocity. It means that you have a U1 and U2 as a two information. So U1, U2 is information, so you have it from the sensors. So the system number 2, it can be represented like this. So the system can be represented like xk plus 1 as a function f of the function x and uk. And this function can be represented like this. fxu is the xk plus this term. Of course, you can see that this function f is nonlinear because of the sine and the cosine. But if you look at equation 3, in equation 3, so this is a nonlinear function, but you have some input data from the sensor, but you need to find x. And this is basically the challenging part, because for this challenging part, so you need to look at the accuracy of your sensor data, and therefore I'm going to talk about how to get a better estimation. But the first problem in estimation x is about the nonlinearity we have from the basically from the function f. Okay, so so if you want to avoid this nonlinearity, you can use the Taylor series expansion. So by using the Taylor series expansion to estimate x at k, so you can basically express equation 3 like this equation 4. In this equation 4, you have a discrete model for the xk, but you have a matrix ak. So this matrix ak, so it's a Jacobian matrix. So you can calculate ak by the partial derivative of the function f respect to x, and then if by calculating this partial derivative. But if you look at x could be equal estimation of the x, so you can basically write this equation. So this matrix you can find, so is you can see that the estimation of the theta will be appeared. So and then you have a two input signal, and this could be give you the matrix AK. Okay, so in this case, so if you put AK in this equation, the problem is the phi k. So if you want to have a good estimation, so this phi k is the error signal, and the phi k is a function f at the estimated signal x at k minus the linear part. It's a nonlinear term minus the linear part, and also here there is additional term as I wrote k represent the higher order terms of the Taylor series expansion. Okay, so if you are using the Taylor series expansion for the different degrees of the approximation, so you can expect to get some errors like this, like a 5K. Okay, so now the problem is about this, about the 5K, because the 5K, if there is attacks or if there is a fault, so this 5K can increase a lot, and therefore this become out of control. So we need to discuss about this more specifically. So what information we have? The information we have, as I told you before, the sensor is a Doppler radar sensors. So let's assume that the number of sensors is L. L Doppler radars, assume that is mounted on the robot, and then this L sensor, they can give you some sensor data. So the position, the point MI, it means the position X and Y in the Cartesian space, X and Y. So these are chosen as the landmarks of the some landmarks around of the robot. Okay, so you know that if you are talking about the autonomous mobile robot, so you should know that in environment there is a landmarks. So the landmarks is some specific position, a specific object with the some position MI. And it depends on you how many landmarks you want to choose. For example, here we have the L sensors. We are choosing the L landmark. It means that each landmarks so could be useful for to work with one sensor. So the landmarks just can be taken for the better orientation or the position of the robot in the environment. And then based on this information, the sensor can obtain from the position respect to the landmarks, the robot start to find the position itself. Okay, so now you have a sensors, you have a landmarks. So now you need to know what the data you get from the radar sensors. So the radar sensor, I told you that it gives you the Doppler frequency shift data. But the Doppler frequency shift means that the sensor number I, so they can give you the Doppler frequency shift and also the azimuth information. Okay, so two information. So the Doppler frequency shift and also the azimuth information from the landmark number I. So these two data, these are the two data you can get from each sensor, and each sensor find this particular information respect to the landmark number I, and therefore you have these two data. So if you want to see from the mathematics, so it means that at the time instant k, so you have a measure Doppler frequency shift, measured Doppler frequency shift BIK, and also the azimuth information phi k. So these two, the information from the landmark I, so we call the measurement. Okay, so now if you have some cyber security attacks, so these two information can be changed, can be manipulated, and therefore your estimation should be robust. How to get a robust estimation in order to avoid any problem, any such a problem from the attacks is a very challenging topic. So now I want to talk about the sensor modeling. You know that you need to pay attention that if you are using the Doppler radar sensor, you need to develop the measurement model or the sensor model. So let's assume that for the sensor number I, for the radar number I, so the measurement is a Zi bar k. So this information is a nonlinear function of the two information. One is the position x, and also the position R for the MI, okay? Position of the robot and position of the landmark, and based on the function J, so you can find two information, DIK, the Doppler frequency shift, and phi ik is azimuth information. Okay, so this is the reverse problem. This it means that you have this, you have VIK, phi ik. Now you need to find xk because the MI is given, but you don't have this. And therefore, you need to find the basic with the estimation. So, but if you are using the Doppler radar sensors, so the function Jx, you can write it down for the position of the basically the robot or the vehicle respect the landmark number I. It means that this mathematical model can be written. In this mathematical model, you know that x and I, y and I is the position of the landmarks, x and the theta and y is the position of the robot in the basically for the case of the kinematics. And also there is some other parameters like fc, and this parameter is the radar carrier frequency, and the parameter c is the speed of the light. Okay, so this mathematical model, so it gives you the sound relation between the sensor data and also the position you want to obtain. But please pay attention that this is a nonlinear function, and at any time you could get some wrong data, and then how to get the good estimation is a very big problem in the context of the automated mobile robot or the cars. Okay, so I want to tell you a little bit more about the sensor data. So the sensor data, is a nonlinear function J. But you can approximate it like this. So if you write down the sensor data like a linear term based on the Taylor series expansion, so you can find this the error signal T psi ik, and this is a linear part. And the matrix CIK, so you can calculate it from this Taylor series expansion. You can see, you can take all the derivatives with respect to x, y, and the theta. This is the Jacobian matrix at the estimated xk, x hat k. Okay, so if you calculate this partial derivative, I have written down the disturbance and also in impulsive form. So now you can see that the T psi ik, so I introduce it from this expression. So T psi ik was the approximation error based on the Taylor series expansion. It can be also used to express the linearization error, external noise, and also possible outliers. Okay, this is very important. If there is attacks or the fault in your data, in your sensor, mitigate the network congestion, so you can be native. So now what happened here? So your sensors receive the data from the landmarks, okay? So now the sensor data, it was ZI bar K. You see here I wrote ZI bar K, if you remember here. So ZI bar K is the sensor received at the radar sensor. But this data should be sent through the network, and therefore there is another data, is a ZI arrow K. So ZI arrow K is the sensor data has been received after the network by estimator. Okay, so there are two different data. So now if you are using the round robin protocol, so ZI arrow K, it can be sent in the periodical form. There is a function pi k. So this function pi k, it says that if you are following this mathematical form, it says that the pi k is a sensor that obtain the privilege to access the communication networks. It means that to send all the data, there could be a lot of problems about the congestion, limited bandwidth, and so on. Okay, so now based on equation number 7, you have particular data, so at the estimator, and this data can be used for estimation. So now you have two data. One is the Z. So now you have two data. One is the Z bar K. These are the data at the sensor. So this is a function, and if you write it, like this, so now you can see that these networks is very important because it affects on the data you can receive at estimator. At the same time, so these metrics, phi, arrow, pi, k, it can be represented based on these diagonal metrics term, and also this term, as you noticed before, the T sign arrow K is represent the error in your estimation. So now I'm talking more about this part. Okay, so this is a mathematical model for the actual received data measurement at estimator. Okay, so in equation 8, in this equation, we can see that the ZIK is a useful measurement data to determine the desired estimator, and the other measurements are equal zeros. So this equation number 8 increases the dimension of the measurement data, and there is a lot of computational complexity. So this equation number 8 has some drawbacks in terms of computational complexity in the real-time mobile robot. Okay, so if we want to reduce the computational complexity, so you can follow equation number 9. So in equation number 9, so there could be some sort of the representation. So based on and to find the relation of the zk equals ck xk plus t psi k, and the ck it has such a representation. Okay, it means that you can include the information of the network in your two metrics C and also the new function T psi, and therefore this equation is not linear. It's a saturation to deal with the cyber attack. Is responsible to deal with the measurement outliers. If the attack exists and this want to increase, so this function will be saturated, and then you can avoid any problem in the estimation. So the saturation function sigma k, it has a two levels, sigma 1, sigma 2. There are two functions like this. And I can tell you that the first term can be introduced like this, sigma tau k, is from this mathematical formulation. But please pay attention by yourself. Vector qk, it contains the sigma k. Vector qk, it contains the sigma k, and t psi k is the outlier information, and also some term of the saturation function like this. So we take it in the vector qk. So the vector qk exists here in equation 13a, and also in equation 13b you have this sigma k. So now this is a nonlinear function and also time varying, and then we need to think about how to make the convergence of this estimator. So there is some objective function in this design. The objective is to design a time varying state estimator in the form of the equation 10 I showed you before for the mobile robot system. So more specifically, we are interested in looking for the estimator parameter L, lambda, matrix R, matrix W, such that the aerodynamic system, and you need to satisfy this performance index by choosing the parameter. You don't know it. You need to design it. You need to design these parameters. So you need to look at the aerodynamics. I showed you before aerodynamics for the state estimation and also for the evolution dynamics. So the HMDT performance condition should be satisfied. I showed you before, it means this HMDT condition. So this should be satisfied. So if there exists a family of the positive different matrices, if there is such a matrix, to the following the recursive LMI. LMI is a linear matrix inequality, but we have some recursive LMIs. So this should be satisfied. Matrix EK should be negative, and this is your matrix EK. Okay, so this matrix should be negative, and this is the time varying. And then finally, you can also satisfy this condition for the initial condition, and finally, you can obtain the result. Okay, so the second part is this was about the satisfaction of the HMP condition, but now I need to show you how to design the parameters because you need to find basically the observer gain. So again, for the same strategy, there is another theorem. It says that if you solve this LMI problem number 16, so in this case, there is some LMI variables like the matrix PK. It means LMI should be solved at each iteration. At each iteration, you can find a new L because L is a time varying. And then you can design your time varying estimator. Okay, so there is an algorithm to solve this problem. First, we need to give some initial conditions. So like the HNT performance, the gamma I told you before, and there is some initial values for the LMI variables. And then you need to solve this LMI number 16 in the recursive form and then to obtain all of this information. And then when you obtain this information, you can calculate L. I'll show you before. L is the P inverse multiplied K, okay? So then you can repeat it and repeat it basically to get the estimated values. Okay, so let's a little bit discuss about the case of without measurement outliers. So here I talk about the outliers like cybersecurity, but if there is no cybersecurity, a sigma goes to infinity. So if the sigma goes to infinity, it means that you don't have any attacks. So then you have seen in other courses. In other courses, when you design this estimator like a Kalman or a Newmaker observer, if you avoid this saturation term, it means that you have this mathematical model. Mathematical model number 18, it means that the sigma goes to infinity just in the case of that there is no outliers. So, okay, and you know about this, and that's it. I can repeat it again. So for this particular case, you can also develop the error signal. You can develop the evolution dynamics for the error signal. And now you can see that there is no evolution for sigma because sigma is infinity, okay? But only you have this H infinity condition. This H infinity condition means that you need to satisfy or mitigate the energy of the disturbance over the error signal. So this problem is relatively simple because there is no sigma. This is only the time rank estimator. The same theorem, so you can adapt it for this case, but it is very similar what I proposed before. Now I want to show you some simulation result. Let's assume that we have a simulation for 300 samples for the horizon N samples. And then there are three Doppler radar sensors on the mobile robot. And then you can follow some sort of the profile. So let's assume that the robot should follow some particular position. For this sampling time, the speed should be 400, and also the angular velocity should be this. And for this time, the robot should follow the speed of the 400 and also this angular velocity. It means that we can give some particular set point. So the robot should track this information. So these are the initial conditions for this problem simulation. And this information, because you have a three sensors, then you have a three landmarks, N1, N2, N3. You see, all the information is given. And then you can start with the initial values for the evolution dynamics of the sigma k. And this is the starting point for your LMI, basically solving the LMI. Okay. So if you start, and here the H integrity is this mass activation level, the gamma is this parameter, and because based on this parameter, you can basically find a feasible solution for the LMI you have. Okay, so these are the some index function. So index function, if you want to see how much your result is accurate, you need to compare, you need to look at the error signal in this to the calculation. These are the sum Euclidean the distance and also for the theta. So you need to measure this, you need to calculate this index function just to show that how much error you have in the calculation based on estimation and the real parameter. Okay, so based on this Euclidean function, you can write down the two error, mean error, so for the position and also for the angles, and you need to evaluate. So how much your estimator is robust, and this is something to show the accuracy of your result. Okay, so even you can use the maximum values of the ME and M theta. These are the two different index functions. You can choose both. You can choose the mean value, you can choose the maximum deviation, and both are okay. Depends on you if you want to do the better analysis of your result. Okay, so based on this table, you can see that if you have a noise or you have a noisy data in your file, okay, so the basically in your estimation error, if represented with a different level of the noise, you can see that the error in the mean value and also the maximum values, so they also increase. If the noise increase, so now you can see that these error values also increased, and it means that the noise or the cyber attacks they make a very important effect on your estimation part, on the error estimation. So these are the some values for the parameter of the LMI values, because if you solve the theorem by using the LMIs, at any iteration k, 1, 2, 3, and so on, for different time, you can find different metrics L for estimators and also other parameters for the LMI. Okay, so you need to solve LMI at each iteration. But if you are not familiar with LMI, so I can provide you maybe some other lectures, or I can provide you some MATLAB code in order to solve this problem. But if you solve this problem, you can get all this information. And this is a picture about the actual mobile robot trajectory and its estimation. So now you can see that there are two curves, is the actual trajectory and also estimated. So you see that the red one is trying to follow the actual trajectories. And this is also the tracking of the actual, also respect to estimation for the angular, for the angle you can see for the theta, and you can follow the estimation. And the result is quite good. And because here we have the sigma value. The sigma values, it was you remember that it was has a two sigma 1, sigma 2. So the sigma 1 is for the measurement outliers. So for the frequency Doppler shift, and the sigma 2 is handling the outliers on the azimuth information. So now you can see that the both sigma 1, sigma 2 has such a profile, and they are active. You can see that there are some variation in the sigma, it works and try to protect your estimators. So now I want to show you that if there's attacks, what will happen? Assume that at the time K90 and K280, so there could be some outliers in your data. So now you can model as a disturbance, as a noise, or as an impulse function. So now there could be such a problem at this time. So now you see that at the time 90 and 280, so now we can see that there are three plots. Blue line is the actual trajectory, red line is estimated based on the algorithm number 1, and the blue dash line is estimated based on algorithm number 2. So the algorithm number one, it can handle basically the attacks. And then you can see that the red line, so it is very smooth. There is no any spikes. Red is very smooth and they can follow the blue line. Why? Because in your mathematical estimator, you have used a sigma, and the sigma can control the deviation. But if you look at the black line, so the black line, the dashed line is a no any sigma. If you are using the regular estimator, then you can see that the attacks, they can change your position of the robot, and this is basically the problem. So now for the position, you can see at the time 90 and the time 280, there are two spikes. So these two spikes, because you didn't consider sigma. If you take the sigma, you can get the red signal. The red signal, it is more robust. And this is the reason that for the cybersecurity, you need to use some advanced estimator. An advanced estimator, one could be like this I presented today. So the same is also for the angles. For the angle, you can see that if you are not using the sigma, you can get these spikes. But the red signal, you can see there is no spikes, and therefore your approximate your estimation is correct. So now the sigma, sigma 1, sigma 2, they have such a behavior. Exactly, you can see that at the time 90 and 270, so these two spikes in the sigma, they are responsible to control the attacks. And this is the reason that you need to pay attention to look at this problem. Okay, I think there is no time to go to this part. Maybe of course, I can provide you this material, but I can stop at this point. So maybe we can have a 5 minutes break. If there is no question, we can have a 5 minutes break, and after break, we can continue to the second part. Any question? Okay, so if no question, so we can stop here, but I can provide you this material for fusion estimation. You can study by yourself, and if you have questions, you can contact me. But we can stop this part because we have another part for today. I want to present it after the 5 minutes break. Okay, we can meet in 5 minutes. Okay, thank you. Okay, so welcome back to the course. If there is no question, so I can start to go to the second part of the lecture today. So in the second part, I want to talk about some topics related to the HMPP control, basically for some application to the multi-agent systems. And also, I will discuss about some effect of the event triggering control in cooperation, basically with the model predictive control, and also for the multi-agent system. And also, I will talk about some multi-formation tracking for the network robotic system. So the lecture today, so the main focus is on some new technology we have, basically for control of the multi-agent, and based on some development on the event-based control with some advanced control techniques. So, but if you need more information, you can contact me because each part there are some requirements for you to follow the material. But and I have already mentioned the reference. But later on, if you find any difficulties to follow the material, you can contact me. So the first introduction. So introduction, we know about the network control is the history of the control come from the analog control to the centralized digital control system, as we discussed before in the context of the network control. We have a topic of the decentralized control. This was the starting point. And then the decentralized control, we notice that there are some basic advantages in the handling the basic the system, but there could be some issues from the network side. And therefore, the distributed control system DCS was introduced as a potential application to the manufacturing process control. So because in the DCS, you have two parts. One, you have a network for communication and the monitoring. And then you can see that how to look at the network complexity is some challenge we have in the distributed control. So the feed-bus control system FCS was introduced after DCS and then the ICCS is an integration of the control and communication 1988, and then the network control in 1998, and then coming to the CPS. As we are talking about the CPS, it means the control, actuators, sensors, basically are integrated with some digital blocks evolving according to discrete events as a cyber. So it means that this integration of the basic this component, it can basically can introduce the CPS. So these are the development of the control systems. So that's it. We are talking about the network. We talked about the network control as a distributed, as a complete distributed. So as you see in this case, we talked also in the previous lectures. So you can use this structure also for the estimators. But there is some integration of the sensor, controllers, and also actuators. But you should think about different configurations. So you see that the data will be sent over the networks. So you can also think about the distributed the filtering system. So it means that you have a target plan, you have a sensors, you have a filtering, and then you can get some error signals. So if you want to take it to the network-based filtering, so you need to take your sensor data over the network. So now you can see that in both cases, so in the case of the network control system or the network-based filtering, so there are some issues about the networks and there are a lot of complexity. And always in this course, we talk about the complexity of the networks. Okay, so we noticed that in the network, there are some issues about the time delay, packet disorder, packet output quantization, And this could be they can provide some nonlinear physical plan. So if the network will be considered, the system is a totally nonlinear, and then there could be some challenge to classical control theory. So that's it is difficult to design the control. So you need to learn how to deal with this complexity in the control theory and how to design the stable control methods to deal with this problem. Okay, so another topic I want to introduce from the CPS for the larger scale could be some context of the multi-agent system. So multi-agent system are systems that consist of the multiple agent, so with several sensor actuators and the capability to communicate with each other. So now you can see that in the context of the multi-agent, so you need to look at the the data from the sensors, how the actuators can react to the sensor, to the controller, and all the communication between the agent is through the networks. So there are some applications. So basically, the several applications for the multi-agent, like the automated highway, emergency patient transportation, so air traffic control, satellite formation, robotic formation, flight formation. So now you see that you could expect so many applications for the multi-agent system. So one application could be also interesting to discuss is about the multi-agent system in intelligent manufacturing. So there is the cyber physical system. So architecture integrate the production and quality control in the multi-state production line. So this is a production line. You see there a lot of a station number N, on this distributed, and this is a concept to look at the control strategy, a concept to look at the control strategies. So they're based on some features from the networks, some event-based. It means that we should be discussed in this context. So the traditional control is a point-to-point control. You see the data from the sensor go to the controller. It's a classical control. But if you come to the distributed control, you can see that the P1 to Pn is a distributed plans, and then all the measured data Y1 up to Yn can be sent to the communication networks to the different controllers. But please pay attention that the input to each controller, for example, C1, is the measurement Y1 and also some neighbor data. So here the Yj belong to the set N1T. What does it mean N1T? The N1T is the neighbor plans, neighbor system to the system number 1. And from the neighbor system, so there is some additional information. So it means that we don't need to get all the information for the sensor, for the control 1. Only you need to look at some information from the neighbor system. But this could be sort of a distributed system over the networks. So another topic we have in the multi-agent is a multi-agent formation. It means that you have a group of the agent with some specific task. So if the agent has a specific task, they can do some formation. For example, for this system, so if you have this multi-agent system, if they go to the formation stabilization, they can come to this shape, okay? It's a triangular shape, and this is a multi-agent formation. So in the multi-agent formation, you need to look at the position and of each agent. So for the agent number I, so you can see that you have a position Pi, you can get the velocity. So in this case, you can also design you can think about how to control basically this position. And therefore the control of this is a very simple dynamics. So for each agent, you can maybe you can think about this simple dynamics, how to design the control signal UI to get one particular position for agent number I. So these are the some textbooks if you want to look at some fundamental aspect of the formation control. So formation control, it can be also used in the robotics, basically the self-assembly. You see that how to reach from the centralized control to the decentralized control. And basically in the history, you can see that how the manufacturing system or the industrial or the assembly machines has been developed. So you can see that from traditional robot assembly in the centralized control to the programmable vector field, and if you come to self-assembly, then the formation control. So now the formation control, you are very close to the decentralized control, and that's it, the multi-agent formation control. So basically, we are talking about the fully decentralized control, but only the point is that in this context, there are many complexities based on the security of the data, based on the network data. So, and also in terms of the control, because the system should do some tasks. So another project we did also in the past about the structural vibration control. So I give you some additional information to see that how this can be worked in the context of the multi-agent. So maybe also this is also useful in India. Maybe there are many earthquakes in the north of the India. So the building should be protected. If you want to protect the building against the earthquake, so you can add some actuation device. You can see. So these actuation are distributed actuators. And then if you want to control, it's difficult because you need to give some data. So for the control design. But how to look at the control design? For example, you can partition the whole system to the many subsystems from subsystem 1 to the subsystem R, and each subsystem has some neighbor systems, or we call it the floor or story. So if you want to control the subsystem R, so for example, you have the information YR, maybe the position of the floor, number R, but there could be some other information for other subsystems. But the point is that for controlling the subsystem R, so you can design some advanced control. For example, you can take the YR data to this control agent, and control agent, you can basically design the control for this subsystem R. So maybe you can follow some idea from multi-agent for such as the replicator dynamics. It means that you can design some control based on the local information and also based on the neighbor information. And this is the task in the multi-agent. You need to look at your data. Okay, so the control of the multi-agent from the theoretical point of view, so you have many subsystems. So some individual subsystems, they can only access the information of their neighbor because of the communication constraint. So you have some limitation over the data from the neighbor system. And therefore, the system has to be controlled by a distributed control protocol. So we call it the nearest neighbor rule. Okay, so these neighbor information, so can be taken to the account, and all the agents in the group, they should have a common objective. So in the multi-agent, all the agents have a common objective. So they're leading to the collective behaviors, and the global behavior of the system is jointly dictated by the system dynamics and the communication topology. So now you see that the total behavior of the multi-agent system depends on the network and also depends on the dynamic of the agents. So the basic control problem for the multi-agent is a consensus. Consensus is a basic problem, and maybe I'll talk more about this today. So for the consensus problem, so you could realize it based on the leaderless consensus problem. it means that there is no leader, there is no any external information, and then the output of all the agent of the multi-agent system asymptotically approach a common trajectory via distributed control law. Okay, there is no external information, and the information of each agent, the output of each agent, should asymptotically approach a common trajectories based on the control design. There is another consensus problem. It's a leader following consensus problem. But this leader following consensus problem, there is a leader information, and other followers, they should follow the information given by the leader. And for different agent, we call it a heterogeneous agent. But if the AI are the same for all the agents, these are non-heterogeneous. So these are the two different keywords. So here the UI is the control signal for the agent number I. Omega IT is the disturbance for the agent number I. And we assume that this agent is a controllable, AI, BI is a stabilizable. Do you remember yesterday? Yesterday I talked about a stabilizable. Do you remember? This is a very important topic. AI, BI is stabilizable, and AI CI is detectable. So these two topics I explained you yesterday. These are different from controllable and also observable. Here we call it stabilizable and detectable. So these are the important concepts in control. So we can define the leader dynamics from equation number 3. If we look at the leader dynamics, you can see that there is one state variable T psi O. There is some metric S and R. These two matrices, so they can define the information profile of the output of the leader agent. So the YO is the output of the leader agent, and then this output depends to these two matrices. Okay. So here also the real part of we have also some assumption. So basically, we have also some assumption on the metric S and R you can see here. Okay, so now based on this information of the leader and also the dynamics, it means that there is the one route from the leader to all the agents. For example, here there is a spanning tree because information from the leader, it can reach to other agents, you see. And this means that we have access to this leader, they have access to all the agents. So this is one assumption that we say that there is a spanning tree with the leader as its roots, and this is the meaning of the spanning tree. So another assumption is that all the agents are time synchronized with the sampling the period at each time instance. So now this is important that the agent or the time is synchronized. So it means that there is no any asynchronous basically in the data transmission for the networks. So another assumption, so based on this assumption number 4, assumption number 5, it says that you can let the sampling time tau k. This sampling time, the difference between the two time instance, so tk plus 1 the tk. So and then here you have a sampling period tau k. So this sampling period takes the values from the set the t1 to tn. And then the tj are the sum allowable sampling period. So this assumption number 5, it says that so all the agent they can take they can take the next sampling time, because you need to know what is the next sampling time or the next time instant. So the next time instant for each agent depends on the tau k, and the tau k is one of the values from the t1 to tn, and this tj is we call it as the sampling periods. How much ti, so it could be basically the allowed for each agent to be taken, and they should take it from the set number the set 5. So let's back to the followers, to the agents. So the agents, so they can be representing the discrete time like this, based on the same. So now you discrete time the agent, and there could be different categorization of system. It means that because in previous slide, when you discretize because in previous slide, when you discretize the matrix K,